Okay, let's unpack this. Like, how do we actually bake wood chips into natural gas? Welcome to today's deep dive, everyone.
Yeah, we are jumping right into the heavy chemistry today.
We really are. So for you listening, our mission today is to decode this plain English engineering guide on the Sungas bio-CNG audit. We want to unpack the exact math and, well, the chemistry of how a facility turns leftover waste wood into actual commercial truck fuel.
Which, I mean, it sounds completely wild, right?
Yeah.
But it's just elegant chemistry. We aren't simply burning the wood.
Right, because if you just burn it, you just get ash.
Exactly. We're breaking down solid matter and completely reassembling it at the molecular level.
And the source uses this really brilliant bakery analogy to explain it. They use 8 gasifier ovens that basically they consume 11.52 metric tons of dry pine every single day.
Yeah, and they restrict the oxygen in there so the wood doesn't actually catch fire.
Right, which outputs this raw syngas. But here's where it gets really interesting. There is a problem right out of the oven.
There is. The initial gas mix is, it's flawed. It yields roughly a 1-to-1 ratio of hydrogen to carbon monoxide.
But to make the final fuel, you need a 3-to-1 ratio, right?
You absolutely need a 3-to-1 ratio for the biomethane.
So wait, how do engineers fix a recipe once it's already baking?
Well, what's fascinating here is a process they call the water gas shift. They don't throw the batch out, they just adapt it.
Oh, okay.
By injecting steam, just pure H2O, and mixing it with the carbon monoxide, they force this molecular swap.
Oh, wow. So the carbon monoxide basically steals oxygen from the steam.
Exactly. It becomes inert carbon dioxide and leaves behind the pure hydrogen we need.
That is wild. You just use steam to hack the molecules to get that magical 3-to-1 ratio.
Yeah, and then through methanation, that perfectly balanced mix yields exactly 5,702.4 cubic meters of final biomethane every 24 hours.
Okay, but having a massive cloud of gas is super hard to visualize. Like, how does that actually get a logging truck moving?
Right, we have to translate those cubic meters into a real-world equivalent to see its true value. Engineers call this thermodynamic equivalence.
Because we need to know how much actual heat energy is hiding inside that cloud.
Right, precisely. The daily gas yield holds 204,260 megajoules of energy.
Okay, and in terms of liquid fuel?
That matches the exact driving energy of 5,705 liters of commercial diesel.
Wait, really? Over 5,000 liters? Then why bother with diesel at all? Like, why not just run the trucks entirely on the green gas?
Well, it comes down to density, physical space. Gas is far less dense than liquid diesel.
Oh, so the tanks would have to be enormous.
Exactly. To get the same energy as a standard diesel tank, you would need a gas tank the size of a shipping container strapped to the truck.
Which means absolutely zero room for the actual logs.
Right, which completely defeats the purpose of the business. So instead, they use a clever dual fuel system.
Okay, how does that work?
The engine runs on a blend. It's 60% biomethane gas and 40% regular diesel.
So it's a compromise between going green and staying commercially practical.
Exactly.
So if we know that 60-40 fuel split, what does that actually look like on a real highway?
Let's ground this in reality. The audit applies all this math to a 562-kilometer logging route up in Northland, New Zealand.
And these are not small vehicles. We're talking 58-ton beasts navigating steep terrain. They need about 300 liters of fuel just to make one round trip.
Yeah. Now, apply our 60% rule to that 300 liters. The truck only needs 180 liters of our gas energy per trip.
Okay. And it relies on standard diesel for the remaining 120.
Exactly.
Think about the sheer scale of that for a second. If you take our daily gas pool, that 5,705 liters of diesel equivalent we baked up, and divide it by that 180.
You get roughly 30.
Wow. So this single facility, just processing leftover pine chips, is supporting roughly 30 heavy-duty round trips every single day.
It really highlights the scale of what's possible when you bridge abstract science and practical logistics.
It totally does. And for you listening, this audit is just a perfect example of how abstract chemical equations directly solve massive heavy industry logistics.
Yeah, you really don't need a PhD to understand it.
Not at all. You just need to see how swapping a few molecules literally moves mountains of timber.
And it leaves you at this thought, right? If manipulating a simple 3-to-1 chemical ratio can replace 60% of diesel for massive logging fleets.
Using just leftover pine chips.
Right. What other everyday waste materials are just sitting around just one chemical trick away from fueling our world?